Chapter 7 AC Resistance. This chapter will detail how to perform a transient analysis. Also, you will be able to determine the characteristics of a sinusoidal waveform and determine the resistive response to a sinusoidal waveform. When we talk about transient analysis, this means a time domain analysis in which the x-axis of the waveform graph is time and the y-axis can be any desired value such as a voltage, a current, or power. In this chapter, all responses are plotted in the time domain. In this waveform diagram, we can see the basic points of interest with the peak voltage and VRMS. VRMS is 0.707 of the V peak voltage. It is important in this chapter to understand what a sinusoidal waveform really is. A sinusoidal waveform is a product of circular motion. Since electrical power is conveniently generated by circular motion, sinusoidal waveforms are the basis of the power grid that drives our homes and factories. Another reason why sine waves are special is related to our eyes and ears. These have special receptors that act as variable length tuning forks to sine wave components, allowing us to distinguish various tones and colors. A third reason is strictly mathematical. It turns out the derivative of a sine wave is another sine wave, shifted by 90 degrees. Using this property of sine waves, it is possible to reduce complex differential equations in the time domain to simpler algebraic equations in a frequency domain. Related to this is the ability to break down any shape waveform into an infinite series of sinusoidal components. This is the basis of the branch of mathematics called Fourier analysis. The sine wave that was generated in the previous waveform is shown by this formula, where V is the instantaneous voltage, Vp is the peak voltage, F is the frequency in cycles per second, omega is the angular velocity in radians per second, and T is the time. Now let's move to the first circuit simulation of this chapter. First, we build our simple circuit, which uses a sine wave voltage source V sine in series with a 2K ohm resistor. Now it's time to set our values. We have V off is 0, V amplify is 10, and the frequency of our source is a 1K source. And our resistor is also 2K. We are now ready to set up our simulation profile and run our circuit. We set the simulation profile to have an end time of 2 milliseconds and everything else is set, so we just click apply and run our circuit. Now we want to set our trace as V out and view the output. Seeing that we have a negative 10 to 10 volt voltage range and a 2 millisecond time frame. This can be detailed as your basic sinusoidal waveform shown by OrCAD capture.